All right, so let's start. So I'm going to talk about integrability. So, well, it's actually not the main topic of this Bootstrap workshop, but there are some similarities because we also use some Bootstrap-like axioms to kind of compute quantities. In particular, okay, so the topic of my talk. Well, actually, I probably prefer this big chalk. Is integrability and its relation to n equals 4 super mu theory in 4-dimension. And there will be 6 lectures about integrability, and Pedro is also going to talk about this relation between integrability in n equals 4 super mu theory, which is a maximally supersymmetric 4-dimensional gauge theory. And the main goal of these 6 lectures is to explain how you can compute CFT data in 4D n equals 4 super mu theory. Oh, by the way, this is conformal field theory using the method of integrability, which was originally developed for the 1+1 dimensional system. So this is the plan of my talk. So in today's lecture, in lecture 1, I'm going to give you a general introduction to integrability, in particular, the bootstrappy aspect of integrability, integrable bootstrap. And in the second lecture, I'm going to give you, I'm going to explain how the integrable system arises from this n equals 4 super mu theory. And then, in the third lecture, which is the last lecture of mine, I'm going to do the integrable bootstrap. For n equals 4 super mu theory. So, in all these 3 lectures, I'm basically going to focus on how to compute the spectrum of n equals 4 super mu theory. More specifically, I'm going to explain how to compute conformal dimensions of a class of operators, which is called single trace operators, in large n equals 4 super mu theory using integrability. And Pedro has 3 lectures, and he's going to talk about how to compute correlation functions, in particular the OP coefficients using integrability. So this was the plan of my talk. Okay. Okay, I'm going to push it further. So let me start from the basic. So lecture 1, integrable bootstrap. And let me start by asking this question. What is integrability? So in classical mechanics, there is actually a well-defined notion of integrability, which is often called Liouville integrability. And essentially, in the classical mechanics, integrability means that the integrable system is a particular class of classical mechanics which have the same number of conserved charges as the number of degrees of freedom. For example, one example of integrable classical mechanics is, as you know, the multidimensional harmonic oscillator whose Hamiltonian is given by something like this. M omega squared. So in this system, as you know, of course, we know that the energy is conserved. But in addition to the energy, you can define kind of energy for each direction of the space, and that are separately conserved. So in this system, the number of degrees of freedom is really matching the number of conserved charges, and therefore you can say that this system is integrable. And like there are a bunch of other systems which are not integrable. For example, like if you consider something like a double pendulum, then it's not going to be integrable and it shows chaotic motion. Yeah, something like double pendulum. Okay, so, and this notion of integrability naturally extends to quantum mechanics, but in the quantum mechanics, you need to make sure that those conserved charges are mutually commuting. So in the quantum mechanics, if you have the same number of commuting conserved charges as the number of degrees of freedom, then you can say the system is integrable. Okay, so that's a definition in quantum mechanics, or classical mechanics and quantum mechanics. But what we are interested in is quantum field theory. In quantum field theories, the situation is a little bit more difficult because in quantum field theory, the number of degrees of freedom is infinite. So maybe you might want to define integrability by the existence of infinitely many conserved charges. But of course, comparing infinity with infinity is always difficult, and actually there is no kind of well-defined mathematically rigorous definition of the integrability in quantum field theory, to which everyone agrees. But well, often people just like when people talk about quantum field theory, which is integrable, people often means that it's the system it's the quantum field theory with infinitely many conserved charges. But perhaps some of you or most of you already heard that a kind of different definition of the integrable quantum system, which is in particular based on the S-matrix picture. And there is another often used definition of integrability, which is the factorization of the S-matrix, factorizability of S-matrix. So by which I mean like multi-particle S-matrix factorizes into 2 to 2 S-matrices. So these two definitions, at first sight, looks very different and doesn't seem to be related. But let me begin my lecture by first explaining what is the connection between the two. And by explaining the connection, I will introduce the important notion, which is called the Young-Baxter equation. Yes? In the classical field theory. I don't know. I don't know any nicer definition. Well, of course, in the classical case, things are much cleaner. But still, I don't know any definition which is like something like as rigorous as this classical mechanics case. Okay, so let's talk about the relation between the two. So to understand the relation between the two, let's consider some non-relativistic field theory for simplicity. Non-relativistic 1 plus 1D QFT. And in particular, let's consider 3 to 3 scattering, where you have particle P1 and particle P2 and particle P3 are coming in. and particle momentum P4, particle momentum P5, and particle momentum P3, P6 are coming out. And because it's non-relativistic QFT, first of all, we know that in this process, momentum must be conserved. So there are like two obvious conserved charges. One is the momentum, which you can define in this way, and they are conserved. Sorry, 4 to 6. And so this is momentum. And there is also yet another, of course, charges which conserve. Which is energy. So because I'm considering non-relativistic field theory, energy is essentially just given by the square of momentum. So these two charges always exist, regardless the theories, the integrability of the theory. But now I want to analyze the consequence by imposing. So suppose there are, in addition to these two conserved charges, there are infinitely many conserved charges, which I denoted by QS. So suppose that there are infinitely many conserved charges, which are given by this expression, Pi to S, and they are conserved. 4 to 6, Pj to S, conserved for all possible integer which is greater than 2. And the next thing I want to do is to analyze the consequence of this. So the first consequence is that if you impose the conservation of these like infinitely many charges, then you can immediately show that the set of incoming momentum, P1, P2, and P3, must be equal to the set of outgoing momentum, because otherwise there is no way for you to satisfy these infinitely many conserved charges, conserved relations. So this is one consequence. But this is a kind of, well, not so deep, because it just restricts the kinematics. But I also want to discuss more like a deep dynamical consequence of the existence of infinitely many charges. But in order to do so, it's better to consider the scattering of wave packet. So as you learn in quantum field theory textbook, if you really want to rigorously define the scattering process, you'd better consider the scattering of wave packets rather than the plane wave. So let's consider the scattering of wave packets. And essentially, the wave packet is given by some Gaussian integral over the momentum. And the momentum is peaked around some momentum P. And then the rest is just a plane wave, which I denote it by, which I write it explicitly, plus ikx. And I'm going to denote this phase factor by I to phi, I times phi. And so this is a simple exercise. Because this is Gaussian, you can explicitly do the integral and try to look for the peak of this wave packet. But of course, there is a much simpler way to know the peak of the wave packet, which is just to take the derivative of this phase factor. So what you need to do is to look for the stationary phase, and then finally evaluate k at P, which is the center of this wave packet, the center of this Gaussian in the momentum space. So this defines you the peak of the wave packet. So then let's analyze this peak of the wave packet. So of course, this is just the elementary exercises. So the peak of the wave packet in this case, okay, you just need to take a derivative of this phase factor phi. And if you do it, then you realize that the P peak is essentially given by x minus k over m times t equals 0. Yeah, the position of the peak is defined by this equation. Sorry, I think what I should have said is that the peak of the wave packet is defined by this equation, because you are looking for the stationary phase. So you take the derivative of the phase and then set it to 0. And as you can see, this is nothing but the momentum. So in this way, you can recover the classical motion of the particle. So okay, so far this has been just elementary exercises. Then let's now consider the action of these conserved charges. For instance, let's pick some charge Qs and then exponentiate it, and then act this symmetry generator to the wave function psi. And if you do so, let's, for example, consider the case s equals 1. Then essentially, if you act this factor, then the phase, which was originally e to I phi k, gets modified into e to I phi k plus I times alpha 1 times k, because Q1 is nothing but the momentum. So if it acts on the plane wave, it basically spits out this factor of k. And then you can do the same exercise of like taking this phase factor and then looking for the stationary position of the stationary phase. Then if you do that exercise, then it's not so hard to see that the peak of the wave packet is shifted in this way. But of course, this is kind of what you expected, because as you can see, that what this is telling you is that the effect of the action of this charge is to shift the position by some constant amount, which is of course the physical interpretation of the momentum operator. Okay. So now I can also do the same exercise for s equals 2. For s equals 2, what you get is also simple. So s equals 2, what you get is this kind of phase shift. Phi k is going to I phi k plus I alpha 2 k squared, which basically changes the peak in this way. Sorry, yeah, this is correct. And as you can see, okay, so now there is a factor of k, but as you can see, this factor of alpha 2, you can absorb it by the shift to the shift of t. And this is, of course, again, what you expected, because what I did is to act the Hamiltonian operator, And the effect of the Hamiltonian should be just a shift of the time. But something interesting happens if you consider the action of this charge for s larger than 2. And if s is larger than 2, if you do the same analysis, what you get is alpha minus k over m t plus s alpha s k to s minus 1 equals 0. And now you cannot absorb this extra factor into anything, which means that the shift actually really depends on the momentum of the particle. So this has actually very important consequence. So okay, I just erased the picture I wanted to use, but so this has actually very important consequence. So originally we were thinking about this kind of scattering process, 3-to-3 scattering process, and I was analyzing the consequence of acting some higher charge generator, higher charge symmetry. And I was saying that acting the charge with s larger than 2, you can actually shift the contour, shift the trajectory of the particle in such a way that it depends. The shift depends on the momentum. So, which means that if you take an appropriate linear combination of those charges, so let's write it in this way, and then if you act it on this space-time diagram, then you can basically shift each particle, the trajectory of each particle separately, so that this picture becomes something like this. So this picture basically means that the scattering of 1 and 2 happens here, which is far separated from the point here at which the scattering of P1 and P3 take place. And so this, first of all, and we know that this is a symmetry of the theory. So the S matrix shouldn't change before and after the application of this symmetry generator. So this, first of all, means that 3-to-3 scattering amplitude must factorize into 3 2-to-2 scattering amplitudes. But you can also do something more interesting. So let's take another set of conserved charges and try to move the trajectory of the particle in a different way. And if you do so, you arrive at this picture instead of that picture. But we know that all these three pictures are essentially the same because I was just acting the symmetry of the theory, which means that this and this must be equal. So this is the famous Young-Baxter equation, which constrains the S matrix of 2-to-2 S matrix of integrable quantum field theory. And what I'm going to do for the rest of today's lecture is to explain how to use this Young-Baxter equation to kind of bootstrap the S matrix of some particular quantum field series. So is there any questions so far? Yes?
Put the labels 1, 2, 3 on the...
Yeah, 1, 2, 3.
Do you really have to use infinitely many concept charges?
I think for 3-to-3 probably no. But of course, if you want to say that multi-particle scattering all factorizes into 2-to-2, you do need to use the infinitely many charges. Yes?
So how important in being in 2 dimensions was this?
Okay, yeah, that's a very good question. So you can play the same game also in the higher dimensions, but there is a crucial difference between 2D and higher D. In higher D, if you take arbitrary combination, nice combination of these conserved charges, then you can basically move the trajectory off the plane, which means that now two trajectories are non-intersecting, which means that actually if there is such a like infinitely many charges, the theory must be free. So which is that is the famous like a result by Coleman-Mandula. Of course, like Coleman-Mandula proved it in a more rigorous way, but this is a kind of one intuitive way of understanding it.
The three particles happen that completely constrain the two to S matrix, or would the four particles happen with even more?
I think in integrable quantum field theory, I think if you have the Young-Baxter for 3 to 3, you can also move, like locally move the picture of the 4 to 4 and like change it into the picture that you want. Okay, so this was the basic introduction, and now I'm going to take one example of quantum field theory, integrable quantum field theory, and explain how to fix the S matrix using the integrability, well, actually Young-Baxter equation. But now there are two choices. So, and in order to decide, we need to vote. So you need to tell me which group do you like, ON or E8. So let's vote. So who likes ON? And who likes E8? Okay, so I think like there are many people who preferred ON, so I'm going to talk about ON. I'm sorry, Leonardo. But actually, this was a kind of planned question, because if you look at the web page, then the problem sheet for this first lecture is about ON model. Okay, so I'm going to talk about ON model. So, 2, ON model. So let me first define you what is ON model, what I mean by ON model. So what I mean by ON model is actually ON sigma model. So the field, So the field, I denote the field by, in this way, so yeah, sigma and tau. So sigma and tau are two-dimensional space-time, and this is n-component vector. And it has to satisfy, well, the norm of it is just 1. So it has a unit norm. So this is the field of the ON model that I'm going to study. Okay, so this board doesn't move. All right, so, and the goal of this, the goal of the rest of the lecture today is to determine 2 to 2 S matrix of ON model in particular. I'm going to bootstrap it. So in order to bootstrap it, well, I first need some input, because otherwise I cannot specify that the theory is ON sigma model. So what are the inputs? So let me first write so let me first analyze.
Are you doing relativistic?
Yes, now I'm doing relativistic field theory. So now let's discuss the input. So input 0. So Okay, I haven't written down a Lagrangian of this theory, but from this property, well, this basically is a field living on Sn, Sn minus 1. And because the field is living in Sn minus 1, classically, there are n minus 1 massless bosons. So you have a Sn minus 1, and then you pick some direction, and then if you consider the small fluctuation around it, there are n minus 1 direction. So classically, you may conclude that there are n minus 1 massless bosons. But this is actually wrong, as probably most of you know. And there are many ways to show that it's wrong, but today I'm going to show that it's wrong by doing some large N analysis. So this large N analysis is actually kind of correct, and this gives you an important input of this theory. I'm going to write down the action. So the action that I'm going to use is of this form. So this is the path integral. Sorry, this is not the action, but this is the path integral. The path integral that I'm going to use is this exponential minus s phi and sigma, and s phi sigma is given by this. So there is a overall coupling constant, and you have an ON field. And then there is this term. So this term is essentially Lagrange multiplier. Which forces the norm of the phi I to be 1. Okay, so let's analyze this action or partition function. So the partition function, yeah, you can remove that. That's mine. So, so the partition function, to compute the partition function, you can the first thing you can do is to integrate phi i's, because obviously phi I is just Gaussian. So if you integrate phi I, then you end up with this effective action for sigma, and this effective action is given by 1 over kappa squared d2x minus sigma plus n over 2 log determinant minus Laplacian times plus sigma. Okay, I guess this is just standard exercise. So now the next thing I'm going to do is to take the large N limit, because so far what I just said is correct also for finite N. So the large N limit that I'm going to discuss is as follows. So I take the, Okay, let's see. So the large n limit I'm going to discuss is, of course, defined by this n going to infinity. But in addition to that, I keep something like the Hooft coupling, which is kappa squared times n over 2, fixed. And if you do so, then you immediately see something nice. Because here you have 1 over kappa squared. But in this large n limit, essentially, this becomes proportional to n. If you rewrite it in terms of lambda and n, then you can say that there is something very large in the large n limit in the exponent, so you can approximate this by saddle point. And by taking the saddle point, you get this equation, which is 1 over lambda equals trace of 1 minus delta square plus sigma. And you can compute it using, so here I use the fact that log of determinant of trace is a trace of log. And you can compute it in this way. And so let's call the expectation value of sigma by m squared. Then what you get is, so you get from here 1 over 2 pi log lambda over m, where lambda is a UV cutoff. And by using this relation, you can rewrite this relation in this way. Sorry. So then in the end, what you get is m equals lambda minus e to minus kappa lambda over 2 pi. So this basically gives you the web of sigma. But if you look at the original Lagrangian, sigma couples to phi I in this way. So the fact that sigma develops a web means that actually these phi i's are massive field. And this is, of course, an example of dimensional transmutation. So the mass actually emerges non-perturbatively. And so this basically tells you that the intuition, classical intuition that you have like n minus 1 massless particles is wrong. And quantum mechanically, you should have n massive bosons. So this gives you an input about the spectrum of the theory. Of course, what I did is just large n analysis, but let's assume for now that this is also true for finite n. So there is also, we also need yet another input.
So are you just stating that there's only n massive bosons, or there are also other particles?
Okay, so that's a good point. I'm going to impose that there are no bound states, actually. But this is, of course, not obvious from this analysis, but I also impose that. So the input 2, I'm not going to explain input 2, but input 2 is again classical. So if you analyze the Lagrangian of the classical ON model, so if you analyze the Lagrangian of classical ON sigma model, you can actually construct infinitely many conserved charges. Which means, as I explained, which implies the 2 to 2s matrix should obey Young-Baxter equation. So I'm not gonna, I don't have time to explain this, but okay, let's use this fact and use it to constrain the S matrix. So I should also emphasize that this is just a classical analysis, whereas what I did here is just a large N analysis. And so clearly the range of applicability is completely different. But the strategy I'm going to take is to analyze this model in a certain model in various limits, and then try to extract some important properties from various limits, and then try to combine it to analyze the model non-perturbatively. And this is actually exactly the same strategy as we take for n equals 4 super mu theory.
Just curious, there were n minus 1 massless bosons.
Yes.
But then we got one more massless
Yes,
boson.
yes.
Is that like something deep or just?
Well, I'm not sure.
Like we got one extra.
Well, that's true. That's true. But well, from the beginning, like what I just said over there shouldn't be true because we are in 1 plus 1D, so there shouldn't be like a really Goldstone boson. So this n minus 1 is like a Goldstone boson. But yeah, I don't have any like a deep answer to your question. But okay. So now let's combine these inputs and do the integrable bootstrap. So which is the fun part. Yeah. Actually, I might have been a bit too slow, but okay, so let's do integrable bootstrap. So now section 3. Okay, so, all right, so let's first just talk about like a basics about kinematics. So what I'm going to discuss is 2 to 2s matrix, as I explained. And now we know that there are n different particles, and each carry indices, so we need to keep track of indices. So the S matrix that I'm going to talk about is 2 to 2, like this. And I have P1 here, P2 here, and P1 outgoing and P2 outgoing. So in 1 plus 1D, if you just consider 2 to 2s matrix, because of the two-dimensionality, the incoming momentum and outgoing momentum must be the same. Well, of course, it's even simpler to derive this if you use the infinitely many conserved charges. So this is the definition. And for me, this is the T channel. This direction is T channel, and this direction is the S channel. And the Mandelstam variable S is defined in the usual way. And T is defined in this way. So in 2D, there is no U channel. And S plus T just satisfies this. Okay. So let's now, so this is just kinematics, but to discuss two-dimensional scattering, there is a better way to parameterize the Mandelstam variable, which is called the rapidity variables. So the idea is that, okay, first of all, let's talk about the analytic property of the S matrix in the S plane, where S is the usual Mandelstam variable. And this topic was, I think, covered already several times in this school and in the school last year. And as we know, this S matrix has a two-particle threshold, and it has a branch cut coming from here. And there is also T-channel branch cut, which starts from 0. And so this is essentially, this point is physical S-channel scattering, and this point is physical T-channel scattering. And I'm going to assume that there are no other poles. So this is the structure of the S matrix in the S channel. But now I'm going to introduce what's called rapidity variables, which is related to momentum in this way. So for each momentum, I parameterize it by sinh and cosh. And if I do so, Mandelstam variable is expressed in this way. So cosh square theta 1 minus theta 2 over 2. And I'm going to call this variable theta and then discuss the analytic property in the theta plane. So so if you map this picture to the theta plane, what you get is something like this. So you have 0, and so there is a point I pi, and essentially this branch cut is mapped to here, and this branch cut here is mapped to here. And the whole region, whole outside on the first sheet, is mapped to this strip. So this is often called physical strip. So this was just, of course, this doesn't have any like a deep physical meaning. It's just convenient way of parameterizing the Mandelstam variable. And I'm going to use this variable for the rest of my lecture. So now what I'm going to impose, so I already kind of used one of the inputs, which is the fact that there are n massive bosons and there are no other bound states. And now we also need to use the properties of the S matrix. First of all, there is a unitarity condition. Wow. So usually in quantum field theory, essentially unitarity means that like something like absolute value of S matrix square is smaller than 1. But because I assume there are no bound states and there are also, because I assume that the series is integrable, in this case, the S matrix square is just 1. So let's first write that condition. So the condition is written in terms of theta variable, takes the following form. So S of theta times S of minus theta is proportional to the identity matrix. I just wanted to say that it's a matrix. Yeah, maybe I should use this. So because so there are indices, and of course you need to contract. That's what I meant. So essentially, this is essentially coming from S square equal 1 on physical sheet, on physical scattering. In physical kinematics. Yeah, actually, maybe I should perhaps explain why I impose this condition, because original unitarity is only defined on the physical kinematics. Essentially, what I'm doing here is as follows. So originally, you are only allowed to impose the unitarity condition here, because this point corresponds to the physical scattering. And this point basically corresponds to this point. And what you really do here is to take S matrix and take the conjugate of S matrix and then multiply them together and then say that it's 1. But there is real analyticity property which allows you to relate the conjugate of S matrix here to conjugate of S matrix here, which is essentially like relating this point and this point in this picture. So then it's clear that what you have here is S theta times S minus theta. And I'm just like analytically continuing this relation to the whole physical strip, because which is actually fine, because once you come to this unphysical region, then S minus theta actually goes to the second sheet of the S matrix. So you can actually kind of use this as a definition of the S matrix on the second sheet. So this is how I derive this equation. So this is the unitarity plus real analyticity. And there is, of course, crossing symmetry. So crossing symmetry change S to T. And if I carefully follow the indices, then it means Sijkl theta is Silkji pi minus theta. Yeah, it's actually hard to correctly follow the indices, but what I'm just doing here is to look this picture in this way or in this way. Okay, and then finally, I'm going to impose Young-Baxter. So these are 3 axioms that I'm going to impose. And what I'm going to do now is to analyze the consequences of these conditions. Is there any questions so far? Sorry, yeah, indices are contracted, yes. Yeah, okay. Let's see. So essentially, let's draw the picture. Essentially, okay, I just erased the pictorial way we're representing the S matrix. Essentially, what you are supposed to do is this.
Have you already used the existence of infinite conserved charges here?
So far, no. So that is hidden here, Young-Baxter equation.
But when you wrote down those kinematics, P1, P2?
Actually, oh yeah, so that's a good question. So in 2D, even if you don't use infinitely many conserved charges, you can actually show that P1, P2 must go to P1, P2. That's the case only for a 2 to 2. For 3 to 3, you do need other conserved charges. Okay. Now let's analyze these axioms, but I'm actually going to do it in the opposite order. So I first analyze the Young-Baxter, consequence of Young-Baxter. So let's do it. Step 1, Young-Baxter. Yeah, Young-Baxter. But before doing that, let's introduce some nice pictorial way of representing ONS matrix. So we know this ONS matrix must must preserve the ON symmetry, and there are actually only three different tensor structures that you can write down for 2 to 2, and which I denote in this way. So I have some oval factor here, and then I have something like this. I go into K, L go into J, and I put A theta here, and this, and B theta here, and this. So what I mean by this is delta of IK times delta of LJ. I mean that the indices are contracted. So these are all 3 possibilities that you can write down. And I'm going to use this pictorial notation to analyze the Young-Baxter equation. So let's try to do it. It's actually very simple. let's first consider one particular 3 to 3 scattering in which you have like 1, 2, 3, and 2 must be here. So let's consider this 3 to 3 scattering, and then let's assume that so the particle 1 has this white index, and the particle 2 has this red index. And so incoming of the particle 2 has this index, and incoming of this particle 3, this has this this index. And I also assume that the outgoing indices are ordered in this way. Okay. So now the question is how to kind of consistently connect these indices. And there are actually one way to connect it. So you have to do something like this. So first of all, this has to go here, so it has to turn here, and it has to go like this. And then it's clear that what the last guy does. And it turns out if you fix ordering here and ordering here, this is the only possibility. And now I'm going to impose Young-Baxter, so I need to equate this picture to a different picture, which have this topology. And again, of course, I need to require that the particles are ordered in the same way. So I have a particle like this, and I have a particle like this, and I have a particle like this. So in this picture, okay, so it's kind of easy to figure out that this is a consistent picture. For example, you can draw something like this. Right? But it turns out there is actually yet another picture that you can draw. So what is that picture? And the picture is something like this. So this particle goes this, and this particle goes this, like this, and the last particle moves in this way. Okay. So then let's analyze the consequence of this. So first of all, the first thing you realize that this doesn't give you any constraint on sigma, because sigma is overall factor, and it's common on both sides. So what you can hope to constrain is just A and B. And let's see how A and B appears here. So here I have just like a usual cross. So this just gives you 1. And here there is a scattering of particle 2 and 3. So and the index go in this way. So I have A and theta minus theta 3. And then here again the scattering of index is of the A type. So I have A times, now the scattered particles are 1 and 2. Theta 1 minus theta 2. And on the other hand, so this must be equals to this plus this. And let's analyze this picture. So let's put indices. So here I have, so this must be equal to A theta 1 minus theta 2. And here I have A theta 1 minus theta 3. And here I have 1. And from this picture, I have 1, 3 scattering. So I have A theta 1 minus theta 3. And here I have 2, 3 scattering. So I have A theta 2 minus, let's write it in this way, A theta 2 minus theta 3. So you can clearly see that this analysis basically gives you this constraint on A's. Is it clear? And now, having derived the equation for A's, sorry, I need to push it further. Okay, yeah, maybe I shouldn't. Okay, now it's better. All right, so this is one equation which you can derive from Young-Baxter equation. And this, it's not actually hard to solve this equation. So the idea is to divide both sides by a theta 1 minus theta 2 times a theta 2 minus theta 3 and a theta 1 minus theta 3. And if you do so, you get the equation like this. A theta 1 minus theta 3 equal 1 over a theta 1 minus theta 2 plus 1 over a theta 2 minus theta 3. Right? And this is equivalent to something like ax plus y equal y over ax y, which means that 1 over a theta must be proportional to theta, where c is some constant number. C is some constant number. Okay. So now so this gave you a constraint on A's. So let's analyze a different configuration which gives you a constraint on B. So now the second Young-Baxter configuration. So the second configuration is something like this. So again, I have this picture, and I put particle with the same index here and here. And then I put particle with this index here. And then I put particle with different index here and here. And sorry, here and here. And then I put particles with white index here. Here, okay. You can convince yourself that the only possibility to connect the colors consistently is to do something like this. And if you do so, it's not so. Okay, so let's try to read off what the value of this guy is. So this guy is, so you have like a scattering of 1 and 3. So you have, but now the index structure is of the B type. So you get B theta 1 minus beta theta 3. And here I get A scattering, and the scattering is between 1 and 2. And so you get this expression. And so this is one side of the Young-Baxter equation. And again, there is yet another side. So yet another side of the equation is different scattering, but the same order. So you have particle coming in from here, particle coming in from here, and particle white coming in from here, particle white coming in here, and there is this line. And clearly, these two lines must be connected. So one possibility is to connect in this way. But there is yet another possibility, which is to connect particle in this way. And this gives you A of theta 1 minus theta 2 and B of theta 2 minus theta 3. And this gives you B of theta 2 minus theta 3 times, what is this? So 1, 2, 3. So this is 1 and this is 3. So v of theta 1 minus theta 3. Okay. So then you get the equation which equates this with the sum of this and this. So I don't have time to give you detail, but I claim that the solution to this equation, so this equation can also be solved in a simple way, and the result is minus c times theta plus d, where this c is the same c as we have over there, and d is yet another constant which is unfixed. Okay. Now, okay, yeah, maybe I erased the wrong blackboard, but okay, so now so far, okay, we succeeded in like computing A and B as a in terms of like a two unknown functions. But so far in the analysis, we didn't see any like a dependence on n. Of course, the final result should depend on n because we are studying O and n S matrix. And there is actually yet another set of Young-Baxter equation, which I don't write down because this is actually exercise problem in the afternoon. And if you analyze that Young-Baxter equation, you can actually fix the value of d. All right. So far, so this is everything that we can learn from the Young-Baxter equation. And let me quickly try to, sorry, not input 2. So the step 2, analyze the consequence of the other two axioms. So I first analyze the Young-Baxter equation, and the next step is to analyze the crossing symmetry. So the crossing symmetry, as I said, is the relation between, is basically saying that it's invariant under the exchange of S and T. And if you do the exchange, then theta gets replaced by I pi minus theta. And if you write down the structure of the S matrix and impose this condition, you find that A of theta, so this crossing equation boils down to two equations. One is this equation. So this equation is actually easy to understand because A was related to this kind of contraction of indices, whereas B was related to this kind of contraction of indices. And if you flip the picture by 90 degrees, then A gets replaced by B. And this is what the crossing symmetry says. And there is, of course, yet another constraint, which is the constraint on sigma, which is the overall coefficient. But this also comes from the crossing symmetry. So these two are the consequences of the crossing symmetry. Is this point clear? More or less? Is this point clear? Okay. So roughly speaking, the crossing symmetry exchanges two indices, and then if you want to equate, then you get this equation. So the last step is to impose the unitarity condition. But I'm not going to explain that in detail because that's also in one of those exercise problems. But I'm just going to state the final result. So if you impose the unitarity, so remember unitarity was the statement about S theta times S minus theta equals identity. And if you impose the unitarity, you get equation for the oval coefficient sigma, where this delta is 1 over n minus 2. So this is the result of the unitarity, which you are, so which is actually also in one of those exercise problems in the afternoon. And then you can try to solve this equation together with this equation. Okay, sorry, I didn't explain one important thing. So first of all, we expressed A and B in terms of unknown fixed coefficients C and D. And then if you further impose this condition, and actually D was already determined like this, and if you further impose this condition, you can actually compute C. And C is I times n minus 2 over 2 pi.
This is becoming divergent at n equal to 2. So that is
Right, that's kind of expected because the argument that I presented involves 3 different colors.
okay.
So this doesn't apply to n equal 2. Okay, so I explained that you can get that equation from unitarity, and you can try to solve these combination of this equation and that equation, and as a result, so that's also a part of the exercise in the afternoon, and as a result, let me just write down the final result and finish my lecture today. So the final result for the ON model S matrix is as follows. So the final result is Sijkl theta equals sigma theta times this tensor structure minus theta over 2 pi I delta, this tensor structure plus 2 pi I delta over theta minus I pi times this tensor structure, and sigma theta is given by product of 2 factors, and each factor is given by gamma functions. Times gamma of 1/2 plus delta minus I theta over 2 pi. Okay. So this is the final result. So surprisingly, as a result of solving this equation and this equation, you find that the solution involves a non-trivial function, which is a gamma function. But anyway, so this is the result of the analysis. Okay, that's a good question. But there are actually some degrees of freedom of like multiplying some oval factors, which preserve unitarity and crossing, which is called the CDD factor. But this choice is but you typically, if you multiply that kind of factor, you kind of screw up the analytic property on the physical sheet. But nevertheless, you can also still try to, well, there is still some possibility of like multiplying that factor without changing the property of the physical sheet. But this is in a sense like a minimal choice. So other choices look more complicated. So the claim is that this is the answer for ON model, and you can actually check it against like a large n perturbation theory. That's what Zamolodchikov and Zamolodchikov did in the original paper. So, okay, so this was, yes?
Why did you use that there was no pole in the S-plane?
Why, where?
Yeah, where did you
Okay, so that's a very good question. So, roughly speaking, this functional equation has many solutions. But most of the solutions have extra poles in the physical strip. And the requiring that there are no poles in the physical strip gives you this solution.
Are those poles, should I think of them as factorizing into subamplitude, something like this?
Yeah, it's well, if there is a pole on the physical strip, like it should be some bound state. Well, but actually all of them are also, the derivation of this is actually also in the exercise problem. Yes?
Usually the standard thing is to scatter localized things, but if I wanted to try and do this stuff in higher dimensions naively, I might try to, scatter.
Yeah, that's good. That's a good question.
Surfaces.
Right.
Is there any context in which
Yes. So there is a higher dimensional generalization of Young-Baxter equation, which is called Zamolodchikov's tetrahedron equation, which is the kind of one-dimensional higher version of. No, tetrahedron equation. Tetrahedron. No. It's not something related to NEMA, but so that equation is supposed to describe the scattering of rigid, infinitely long string in 3D. Okay, so basically that's the end of my lecture today. And thank you very much.